Hello and welcome to this Science mini-masterclass. This is part 5 of my Calculations in Chemistry series where we'll be looking at advanced molar calculations. Please note this is for higher tier GCSE students only. I'll be helping you to secure knowledge of the facts and how to apply these accurately to exam questions. As always, there'll be plenty of hints, tips and common errors to watch out for along the way. Let's get cracking. Two triangle equations, the golden triangles of quantitative chemistry that will be in use again today. These having appeared in some of my previous videos, such as concentration calculations and the basics of molar calculations. These are required for use in both chemistry papers, and we have to remember them. There is no chemistry formula sheet, unlike in physics. Couple of extra little bits of information to go alongside these. I talked about moles and Avogadro's constant in my previous video on the basics of moles. We would of course be given Avogadro's constant in the exam if we were required to use it. And for you separate science students, another value that you are required to remember, and that's the molar gas constant. Okay, a separate video on that in due course. Right, to begin with then, let's have a look at what is meant by the limiting reactant. And what I've decided to do here to help you understand this a little bit better is to look at the ingredients of baking a banana bread, or one loaf of banana bread. And in this case, we're going to be looking at what's the limiting ingredient. So I've got my ingredients list here. And let's say, for example, I actually had these quantities for each ingredient. Now, what we can see is based on these quantities compared to the ingredients list, for most of my ingredients, I have 3 times the amount required to bake one loaf. However, for my bananas, I only have twice the amount. The bananas then are therefore my limiting ingredient because they are limiting the number of loaves of banana bread I can bake. Okay, I would only be able to bake a maximum of 2 loaves due to the number of bananas. And that's essentially what we're doing in chemistry when we look at the limiting reactant. However, what we're looking out for is the reactant that's linked to the production of the fewest moles of a particular product. So let's have a look at a scenario then where I've been given the balanced symbol equation for the reaction of ammonium chloride, this one, with calcium hydroxide to produce ammonia, calcium chloride and water. To begin with, we've got our molar ratio shown there. I've put that in above the equation, and this is showing the actual number of moles of reactants and how they are linked to the moles of each product. So this is the ratio, the molar ratio shown here, and that's dictated by the large number in front of the molecule. And remember, if there is no large number in front of the molecule, we assume there is 1 mole of that molecule. If, for example, I were told that I had 1.5 grams of ammonium chloride and 4 grams of calcium hydroxide, and that they are heated together, perhaps I was going to be asked which of the 2 reactants is the limiting reactant, and I'd be given the relative formula masses in the question. The first thing that I would do is to construct a table using my massive Mr. Mole equation triangle to input known values from the question. And I'm going to do this for ammonium chloride versus ammonia. And I'm going to do this for calcium hydroxide versus ammonia. And remember, what I'm trying to work out is whether the ammonium chloride or the calcium hydroxide produces the least moles of ammonia, because that will determine which of the 2 is the limiting reactant. The first step is to calculate the moles of ammonium chloride. And I've done this using the mass from the question and the relative mass, again from the question. Based on the molar ratio, I can tell that if I have 0.0280 moles of ammonium chloride, I would produce the same number of moles of ammonia because it's a 2 to 2 molar ratio. In other words, a 1 to 1 ratio. The next step is to do exactly the same for calcium hydroxide, where I've divided the mass by the relative mass to give me 0.0541 moles of calcium hydroxide. To determine the moles of ammonia, I've had to double this though, because if we go back to the symbol equation, we can see there is a 1 to 2 molar ratio here. So I'd produce twice the number of moles of ammonia for every 1 mole of calcium hydroxide. So I've doubled my moles of calcium hydroxide to give me 0.1082 moles of ammonia. Now I can see that it's ammonium chloride that is linked to the lowest number of moles of ammonia being produced. It's therefore ammonium chloride that is the limiting reactant. We could also say that calcium hydroxide is in excess. To extend this question a little bit further, I might also be asked to calculate the maximum mass of ammonia formed. Now, I'd still need my calculations shown previously to do this next step. I've left my values for my moles in my 2 tables that I constructed, which, by the way, you don't have to draw nice and neatly in your exam, okay? A rough sketch of these tables is fine. I'm basing my calculation for the maximum mass of ammonia on this table because we previously determined that it's ammonium chloride that's the limiting reactant. And to work out the mass, again, I'm using my massive Mr. Mole equation triangle. I'm multiplying the relative mass of 17 by the number of moles, 0.0280, to give me 0.476 grams. Little examiner's tip, and that's to be careful when entering and transferring decimals with your calculator. I quite often see students in their rush to complete questions very often being out by a factor of 10 because they've either entered a number incorrectly to their calculator or perhaps written down a value incorrectly. So then, how might this appear to us in an exam? Well, we've got question 8.4 here, so it's towards the end of the paper and it's a 6-mark question, so it's going to be high demand. And I've used the bug technique to help extract the information, and I've been asked to calculate the maximum mass of copper produced between the reaction of aluminium with copper chloride, and I've also got to determine the limiting reactant as part of my answer. I've been given my reacting masses here and my relative masses here. There's my molar ratio going in above the balanced symbol equation. I've constructed my 2 tables and entered my known values, the molar ratio of course being based on the symbol equation, and the masses and relative masses based on the rest of the question. Now you can see here I've gone straight in and done a unit conversion from a mass of copper because that needs to be in grams. That is a basic skill and an expectation on the higher tier paper with no extra mark being awarded for that. I've calculated my number of moles for aluminium by doing the mass divided by the relative mass. I've used the molar ratio of a 2 to 3 or 1 to 1.5 ratio to get my moles of copper by multiplying 4 by 1.5. I've repeated this step for copper chloride and for copper. Mass of copper divided by relative mass, and seeing as it is a 3 to 3 or 1 to 1 ratio, I've got the same number of moles as copper linked to the moles of copper chloride. I've then gone on to start explaining how I'm going to go about deducing the limiting reactant. And in this case, aluminium is linked to the fewest moles of copper being produced. So aluminium is my limiting reactant. And I've therefore used the moles of copper based on this, 6, multiplied by its relative mass, to give me 381 grams as the maximum mass of copper. 1 mark, 2 marks, 3 marks, 4 marks, 5 marks, and 6 marks. So, same question, but for a different mass of aluminium this time. Have a go at this question, pause the video, and we'll review the answers in a moment. Right then, we had to do our unit conversion for our mass of copper. We then had to calculate our moles of aluminium and moles of copper chloride based on their reactive masses and relative masses. We got a mark for that and a mark for that. This time, 6 moles of aluminium would produce 9 moles of copper based on that 1 to 1.5 ratio, or 2 to 3. Therefore, if 8.996 moles of copper chloride produces 8.996 moles of copper, it's going to be copper chloride that's the limiting reactant this time because it produces fewer moles of copper. 4 marks so far. I'm using 8.996 moles of copper this time, multiplied by its relative mass is going to give me 571.246 grams. One more different scenario for you to have a go at home. Pause the video and I'll review the answers with you in a moment. Answers then. So you get 1 mark for your calculation of 2 moles of lithium and 2.1875 moles of oxygen. My calculation is being shown on the left hand side there. 2 moles of lithium produces 1 mole of lithium oxide. We can see because it's a 4 to 2 ratio, or 2 to 1, so we've halved the number of moles of lithium to give us 1 mole of lithium oxide. And then we've got 2.1875 moles of lithium oxide linked to the same number of moles of oxygen. That gets us a mark. And the limiting reactant is therefore going to be lithium for your 4th mark. And 5 and 6 marks for the final calculation, with the number of moles of lithium oxide taken as 1 multiplied by the relative mass of lithium oxide to give you 30 grams. And that's a wrap. Mission complete on advanced molar calculations. If you found that useful, please do hit that like button. And for more Science Mini Masterclasses, please subscribe to my channel. Join me in part 6, where I'll be looking at how to deduce the balanced symbol equation based on molar ratios. See you in the next one.